Welcome to CPE 350, Chapter 6.1. In this chapter, we're going to solve the heat equation for a transient problem in which one of the spatial dimensions is semi-infinite. What this problem looks like is a rod, unidirectional heat transport, and it's insulated to ensure that we're only transferring in the x direction. And we'll stretch the one finite dimension we have, L, to infinity. And we don't see many infinite rods in real life, but what this actually corresponds to is a situation when the rate of conduction is so slow relative to the length of material in which heat is fluxing that for all apparent terms, the geometry appears semi-infinite. And this is something that would be true of a good thermal insulator. The governing equation is the same as it was in the last chapter because the physics haven't changed. We've got a time derivative and the Laplacian of temperature in the spatial dimension. Okay, so the actual situation of our problem is the initial condition is that the rod is at T0. That's the same as the last chapter. And then at any time greater than T0, we're going to apply a constant temperature source, T1, to the x equals 1 side of the rod. And then that heat source is going to slowly start heating the rod, but the temperature profile will not penetrate all the way into the length of the rod because it's a semi-infinite rod. So those are our conditions, and we'll write them mathematically. Our initial condition is that at any position in the rod and time equal to 0, the temperature throughout the entire rod is T0. Our first boundary condition is this easy one, that at x equals 0, for any time greater than 0, and we'll just call that T, the temperature in the rod at that position is T1. Our second boundary condition, it feels a little dodgy, but we'll just say that for any time greater than 0, the temperature at an infinite distance into the rod is just going to be T0 because the heat hasn't reached that infinite point, and so the temperature won't have changed. And that is the dodgiest mathematical translation we have to make here, but it is correct. The problem here is that there's not an obvious finite length scale to consider. Before we had x equal to L, now we have x equal to infinity, and infinity is not a necessarily useful length scale. So usually we're looking for a non-dimensional definition in which the parameter is placed over a characteristic value for that parameter. And in last week's example, that characteristic length scale was L. This week, we don't have a characteristic length scale. And so we can kind of start thinking about the trick we used last week to construct a characteristic timescale when there was no natural, obvious timescale. And we took the dimensional analysis of alpha and sort of pulled out that time dependence by multiplying by a characteristic length squared. But we're a little scuppered here because we don't have a characteristic time scale and we don't have a characteristic length scale. So we've got to be very creative in our dimensional analysis. And we're going to define a new non-dimensional parameter. It's going to be called eta, and it will be a spatial non-dimensional parameter. And we're going to take advantage of the spatial component of alpha this time. It's got a length squared per second. And so if we multiply by time, and then take the square root, we get a characteristic length scale that has dimensions of meters. So it's a length. So that we just glean from dimensional analysis. And again, when we're choosing these non-dimensional parameters, there's not one limiting answer that's correct. We can choose a variety of different non-dimensional forms that will help us attain a solution. And so it doesn't really matter if you multiply by constants. And so I am going to do that. I'm going to put in this constant of 4 here because it's going to help with our algebra later. And that's perfectly okay to do because I'm defining this non-dimensional parameter to help solve the problem. So this is our definition of our spatial non-dimensional parameter eta. And what we see is that it's actually the non-dimensional parameter for both x and t. So that's a unique characteristic, and that makes it a similarity variable. Okay, so coming back to our initial condition and boundary conditions, we need to non-dimensionalize these using our new parameter eta. And so we'll start by tabulating the values of eta for each of the conditions we have. So for our initial condition, x equals any value x and t equals 0. So if we plug that into our expression for eta, we get a 0 in the denominator, which means that that equals infinity. Likewise, for our first boundary condition, we plug in 0 for x and any value t for t, and we get 0. And for our last condition, again, we plug in infinity for x and t for t, and we get another infinity. So those are our 3 values of eta for this problem. Now we need to choose a non-dimensional form of temperature. And this doesn't matter so much. The simple form we use in the notes is T over T naught. That works. You can also just write it as T minus T naught over T1 minus T naught because that's similar to the ways we've been defining theta in the past. Both ways work, and I'm going to show you that this way works as well. Okay, so using this definition of theta now, I'm going to write out the non-dimensional form of the bounding conditions. So for the initial condition, t equals t naught, and so the numerator in theta is 0. So theta equals 0, and eta equals infinity. So we write that as theta of infinity equals 0. Because again, theta is a function of eta. Likewise, for the boundary condition 1, theta becomes 1. And so theta of eta equal to 0 equals 1. And for the last boundary condition, theta of infinity equals 0. And so what we have is only 2 of the boundary conditions are unique because, I'm going to call it a boundary condition, they're bounding the problem. So the initial condition and boundary condition 2 collapse onto the same form. And this is another characteristic of a similarity solution, and you'll see these emerge when you have semi-infinite geometries. So this is a good sign that we're on the right track. Our next step here is to non-dimensionalize the heat equation. And this, as you know at this point, is a lot of algebra. So we'll start with our parameter eta down here. The definition of eta is given, and then we need to differentiate that with both respect to x and with respect to t. So when we differentiate with respect to t, I'm going to hold x constant, and so that's what that little subscript there means. And in that case, x is constant, so also 4 over alpha square root is a constant. And so the only thing we really have to focus on is getting t correct. And so you just implicitly differentiate with respect to t. And then in the second instance, we differentiate eta implicitly with respect to x, holding t constant, and get an even simpler algebraic expression. And these are what we're going to use to plug into our non-dimensionalized equation here. So starting with the left-hand side of the equation, we expand it using our 2 non-dimensional parameters, theta and eta. And because we're focused on the time derivative, we're actually holding x constant for this eta differentiation. Then we go on, we're looking now at the x derivatives of temperature. And so when we differentiate eta in this instance, we're going to be holding t constant. And again, we're holding t constant. Okay, so we can start plugging into these expressions now. dt d theta is a constant, t1 minus t0. d eta dt is this slightly complicated algebraic expression here. On the right-hand side, we continue on plugging in each of these values into the expression. And the algebra does start to simplify pretty well. The alpha here crosses with the alpha here. The inverse time on this side cancels with the inverse time on this side. T1 minus T0 cancels on both sides. And actually, the only thing we're really left with is a negative sign and a factor of 2. And so our governing differential equation reduces significantly. And because there's only one independent variable, eta, it's an ordinary differential equation. So in this case, non-dimensionalization has taken us from a partial differential equation to an ordinary differential equation, vastly simplifying the process. We'll write it out in sort of the traditional format for differential equations where you put the highest order terms first. And this is second order. And what that means is to solve this differential equation, we only need 2 bounding conditions. There are 3 derivatives here, but it's still a second order linear homogeneous ODE. And why that's significant is we only have 2 bounding conditions, because you'll remember that our initial condition collapsed with one of the boundary conditions into the same exact expression. So the fact that we've reduced the order of our differential equation by 1 and reduced the number of boundary conditions means that this is a well set up similarity problem and we'll be able to solve it.